Alright, hello. We are going to be approaching this physics problem, which is basically about an atwood machine, which is just a pulley with two masses slung over the top of it. And so from looking at this problem, we see masses, and we can see acceleration. So this should instantly tell us that this is going to be a forces problem. So that leads us to, what is a force? Well, Newton's second law is F equals mass times acceleration. So that basically means that it's the mass times acceleration. I'll give an example. So if you have a 1 kilogram block and say it's falling, which means it's going at negative 9.8 meters per second squared, which is the acceleration. Basically, if our y is in the positive, that's going down. Basically, then we can just say this is a force of 9.8 newtons, because it's the mass times the acceleration. So the units of newtons are kilograms, meters per second squared. So this might be a little bit confusing, but basically this part is just mass, and meters per second squared, we should know, is acceleration. Okay, so next, tension, weight, acceleration, gravity, what do all these mean? So, I'll start with tension. Tension is just used with any sort of rope or cable, and it is a force that is acting on an object. So say we have a 1 kilogram block again. So basically, tension is the force that the string exerts on the object to keep it from just falling, you know? And so that brings us into Newton's third law, which is every action or every force basically has an equal and opposite force. So like that's why we are able to stand up and not fall through the ground. The floor is pushing back up on us. So in this case, the string is pulling up on this object while the object is pulling down. So the thing that the object is pulling down with is weight. So weight is going down. I'll label tension with the T. Weight is going down. So we can determine weight by saying mass times acceleration. So in this case, if we have a 1 kilogram mass and we're on Earth, that brings us to gravity, which means on Earth, gravity is 9.8 meters per second squared. But if we're calculating the weight, that's basically the mass times the gravity, which in this case would be 9.8 newtons, which is a force. So for this, to use Newton's second law, we can say the forces, sum of the forces, equal tension minus mg, which is this force, the weight, tension, equals mass times acceleration. So we're just subbing in this for this. So we know that if this block isn't moving, there is no mass or acceleration. So now we can use algebra to manipulate this by adding mg on both sides, and we get T equals mg. We already calculated mg equals 9.8 newtons, so tension equals 9.8 newtons. So now what you saw that I just drew here is called a free body diagram. So a free body diagram, it's in the name, it means free body. So if we have a problem that shows two masses over a thing, i.e. a pulley, free body diagram, we would draw for each of these blocks. And that means it's free from the pulley. So we're not going to draw any pulley. We're going to draw the blocks. I'm going to call this like mass 1 and mass 2. So important part, add the reference. This is plus y. I'm going to say this is plus x. It doesn't matter which ones you do, but you have to have them to be able to calculate what we're going to calculate further in this problem. So if these are connected by strings, we're going to label the forces on these. So these have a force of tension upwards, and they also have a force of m, their mass, times gravity downwards, if we're assuming this is on Earth. Regardless of what planet, you just sub in the gravity, m2g. So that's what a free body diagram is, and the reason why we have this is to separate it from the overall picture to make it more simple, and then from here we could derive equations like t minus m1g equals ma to further then calculate things like acceleration based on these factors. So the last thing I'm going to talk about before we begin to solve this problem is references. So for this problem, we're going to look at two references. So if we look back at the problem, it's saying that the pulley system is being pulled up at the center, so like here, center of the pulley, it's being pulled up at a certain, with a certain amount of force. So we're going to be viewing this as two things. So this is going to be moving up with an acceleration. So likewise, these are going to be moving as well, but the thing that we're going to say is staying constant is going to be the ground. So if we're looking up at these, if mass 2 is heavier, we're going to notice that, or I'll start, sorry, we're not looking up at them. I'm going to start here. So if we're looking down at here, we know that mass 2 is heavier, so it's going to be going down with an acceleration. Mass 1 is going to be going up with an acceleration if it's lighter. So when we look at this, we're going to just see acceleration going upwards and an acceleration going downwards. They're connected by the same string, so that basically means the acceleration is going to be the same, because if you think about it, it's just like the string is accelerating, there's tension in the string, so that means it's not going to like be buckling or anything, or like jumping around, it's accelerating up. So yes, so this will be accelerating around the object. In this, of course, we will set a positive y being upwards. So this would have a value of positive a, and this would have a value of negative a, because it's going downwards. Okay, so now if we look at this, this entire system is going up with another a, which is going to be newtons, which is the force that's pulling it up as specified in the equation, or in the problem. So if we look at this, we will see when we look at these blocks that it's going to be moving up, and this one's going to be still moving down, but it's basically going to be the acceleration of the newtons minus that. And then this one, when it's accelerating up, is going to be accelerating up even more. So it's going to be added on. So for mass 1, I'm going to draw a acceleration from the ground. I'm going to just put dots here. So the acceleration will look like whatever the acceleration of the Newton force upwards is, which is just m times a. So I'm going to just put in newtons, I'll say acceleration is n over m by just multiplying or dividing both sides by m. So we get a value of acceleration, which is n over m, mass being the mass of the entire system. So I can put m1 plus m2 there if we really want to get specific. Then what we're going to do is for mass 1, the acceleration is going up in this block, so we're going to move it all the way up. And this is going to be added. These two accelerations are going to be added. So this is the acceleration of the entire system, and then the acceleration of the individual block. So we're going to add on a, which represents the acceleration of mass 1. So now for mass 2, it gets a little bit more complicated. So for mass 2, we're going to have a negative acceleration, which means that this is going to be going down from the reference of someone sitting here. We do not know if it's going to be going up. That depends on whether this acceleration downwards is greater or less than the acceleration upwards. So I'm going to add the upwards acceleration of the entire system, which is, again, n over m1 plus m2. We get that by doing the Newton's second law, F equals ma. Basically, it's pulled up with the force of Newton. Sorry. F equals ma, and it's pulled up with the force of newtons. Newtons is basically a number of newtons is the same as saying force. So basically, we're going to take the number of newtons, and then we're going to divide it by the mass, which is the mass of the entire system, which is going to be m1 plus m2. So that's where we get this whole thing from, which is just the acceleration of the entire system going upwards. And then, this time, we're going to minus a to account for the direction. So, with this, I think we are ready to solve. So, This is just saying the references from the ground. The references from the system, from the pulley, if you're like standing on top of the pulley, let's say, you would just see A going up and A going down. But if you were from here, you would see the acceleration of the entire system going up plus the acceleration of the individual masses, or minusing them depending on their direction. So now let's start plugging in values. So we see mass 1, I'll just label this 1 because it's smaller, mass 2 are slung over a massless, frictionless pulley and attached to mass 2, both masses resting on the floor. So basically they start on the floor and the string doesn't have any slack, and then it's getting pulled up with a force of 60 and then 125 newtons. I'm going to draw newtons, and that does not look like a 6. Okay. 60 newtons and 125 newtons. So what we're going to do is we're going to recycle our equation that we found here, or these two values of the acceleration from the ground of mass 1 and mass 2. So from the ground, if this is h ref equals 0, just saying that this is the ground where we're standing and looking at this, we're going to see that mass 1, object 1, as we said back here, will have a value of newtons over m1 plus m2. So for simplicity, I'm going to add together m1 and m2. We know that m1 is 2 kilograms and m2 is 5 kilograms. So I'm going to, instead of saying m1 plus m2, I'm going to just add them together and say 7. So this is a force upwards divided by 7, which represents the acceleration of the entire pulley system going upwards. So now what I'm going to do is I'm going to add the acceleration. And the acceleration basically is determined because this one weighs less, so inherently we can know that it's going to be traveling upwards, because this one is going to be pulling down on it from the other side because it weighs more. So this will have a value of negative a. Again, they're the same because it's attached on the same string. The string isn't going to like stretch or anything. That's what we're assuming at least, and it's a massless, frictionless pulley, so there's no other forces acting on it. So for 1, then we have the A of the object. So this entire thing is the acceleration from a ground level, okay, of 1. So now, acceleration of 2 from ground level. Again, we're going to recycle this because it's just the upward velocity of the entire system, as if this were just one giant block that was 7 kilograms. That's where we get the 7 from, because we're adding 2 plus 5. And then what we're going to do is, instead of adding it, we're going to account for the direction of the acceleration of the bigger block by putting a negative in front of it, and we get negative a. So these are the accelerations in references to the floor, but obviously we do not know what this a is. So what we're going to do is we're going to set up our free body diagrams. So I have mass 1 and mass 2. I'm actually going to just label them now by the number of kilograms. 2 kilograms, so this is, again, mass 1, and then mass 2, I'm going to draw a little bit bigger and say it's 5 kilograms. So if we draw a free body diagram for this, we can see that they each have a string attached to them, so there must be a tension pulling it upwards. So we're going to add a force vector of tension. Force vector just means an arrow showing the direction of tension. So, very important thing. Again, like I said back here, we need to add a reference for which directions are which. So I've decided that I'm going to make upwards positive y. We aren't moving side to side, so it doesn't matter where our positive x is, but just saying that. So now that we know this is positive x, we know tension is going upwards. Tension is going upwards. So now the only thing pulling down on it is the mass itself, which is going to be m times g, because g is the acceleration, assuming that we're on Earth. So, assuming that we're on Earth, this would have a value of 2 times g, because F equals mass times acceleration. Mass is 2, acceleration is gravity. Again, this time we're going to put 5g, because the mass is 5, the acceleration is still gravity. So, now that we have all these, what we're going to do is we're going to set up two equations taking into account the acceleration from the ground and the forces we calculated or just drew with our free body diagrams. So, I'm going to start with mass 1, which is equal to 2 kilograms. So if we look at this, we have a tension force on top, and we have 2 gravity on the bottom. So I have stated that the positive y direction is upwards. So what I'm going to write is the sum of the forces. That means sum of forces, it doesn't matter. I'm going to say forces of mass 1 equal, we have our t, and now 2g is being subtracted from it because it's going the opposite direction. So we have t minus 2 times the gravity. And this, of course, will equal our mass, which we know is 2 kilograms, times the acceleration of the thing from our reference, because it wants it relative to the floor. Here's the floor. This is us on the floor. We're looking up at it. We already calculated that this acceleration is going to be n over 7, n being the number of newtons, plus a. So we have n over 7 plus a. So from here, we need to add our second equation I'm going to do in red for mass 2. Mass 2 is 5 kilograms this time. So 5 kilograms in our 5 kilogram mass 2, it is being pulled up by tension. So we have, again, forces of mass 2 equals tension. This time, instead of 2g, we're going to have 5g because it's being pulled down by 5 times the force of gravity because it has a mass of 5 instead of g. And then we need the ma. So this, again, was the mass, and this is the acceleration that we're looking for. So we need our mass, which we know is 5 kilograms. And the acceleration we're looking for is the acceleration in terms of the ground, which we, again, calculated to be n over 7 minus a. This time we're subtracting a because this mass is predicted to move downwards when looked at from the reference of here because it weighs more. And if one mass is going up, the other one can't go up unless there's another external force pushing on it, which in this case there is. But if we're only looking at the reference of the pulley, then there's not. So we have n over 7 minus a. So this is the acceleration, that's the acceleration. So if we look here, we don't really have to worry about this part. We don't really care about that. What we're going to do now is we're going to solve for our variable, which the question is asking, which is a. So to solve for this, as we see, we have two unknowns, t and a. So what we're going to do is we're going to solve one equation for t and then plug it into the other one. So I'll do this as an example. So if I have t and I add 2g to both sides, we get t equals 2g plus 2 times n over 7 plus a. So now if we take this, which I've just gotten from taking this 2g and putting it on that side of the equation, if we take this t and fill it in for the t in our second equation, then what we can do is we can solve for the value of a. So I'm going to take this and plug it into the second equation, and from there I will get 2g plus 2 times, okay, I'm actually going to go on the next page to draw this out because it'll just take a while. 2g plus 2n over 7 plus a, and then minus 5g equals 5 times n over 7 minus a equals 5 times n over 7 minus a. So now that we've combined both of our equations, what I'm going to do is I'm going to factor out our 2 here and factor out the 5 here. So that leaves us with 2g plus 2n over 7 plus 2a minus 5g equals 5n over 7 minus 5a. From here, we can very simply solve for a by putting the a on this side, and then we're going to put everything else on the other side by adding or subtracting it. So when we finalize this, we get 7a is equal to 5n over 7 minus 2n over 7 minus 2g plus 5g. And as we notice, we have a lot of like terms. So again, I'm going to simplify this once more by subtracting 5 from 2 because they both have n and 7 on them. 5 minus 2 is 3. And 5 minus 2, these both have g, so I can do this. 5 minus 2 is 3. Sorry, plus 3g because 5 is greater than 2. And then that is equal to 7a. So to get our value of a, we take 3n over 7 plus 3g over 7, all over 7. So now if we go back and look at what a actually represents, a is only the acceleration from the perspective of this, but we want the acceleration from the perspective of the floor. So what we're going to do is we're going to plug it back into our equations. And first off, we also need to know our forces. I've left it as n, but now instead of n, we're going to plug in 60 and 125. So I'm going to rewrite this equation, and I'm going to simplify some things in this equation. So instead of 3n over 7 over 7, I'm going to do 3n over 49, because 7 times 7 is 49. And then we're going to add, from the other page, 3g, and we're still dividing it by 7. 3g over 7. So now, if we know that n is equal to 60, and then n is also equal to 120, these are both in newtons, that's what my n stands for, kind of confusing, sorry about that. So, basically, this would mean that our value of a for the first one is 3 times 60 over 49, that's supposed to be parentheses, plus 3g over 7. And when we plug that into a calculator, we should get a value of 7.87 meters per second squared. So now, again, this is only the value of the acceleration with reference to this. We want to find it to the ground, so then we're going to take our value of a and then just put it into these two equations. So, for mass 1 in question I, which is 60 newtons, basically we have n, which is 60 over 7, which we have gotten from this that we derived before, n over 7, 60 over 7, plus our value of a, which we have just calculated to be 7.87, and that gives us an answer for I. Mass 1 will be moving at a speed, velocity is, sorry, not velocity, acceleration, not speed, acceleration of 16.44 meters per second. So, next what we're going to do is we're going to look at mass 2 in the same problem. So we still have 60 newtons, the acceleration is still this, only this time it's negative, so instead of adding 60, or adding 7.87, we're going to subtract 7.87, which gives us a value, m2 will have a of 60 over 7 minus 7.87 is around 0.696 meters per second. I forgot to square this. This is squared. This is an acceleration, not a velocity. We need to remember to square it. So this gives us our answers for I. So for question I, it's asking the same exact thing, except n equals 120 newtons. So we're going to, sorry, not 120, 125 newtons, 125 newtons, 125 newtons, 125 newtons. Sorry for my mistake. So this time, instead of putting 3n being 60, we're going to have n be 125. So 3 times 125, again, we're just using our equation, over 7. And then we had, sorry, not over 7, each. 49, because it's 7 divided by 7, plus 3g over 7. And this gives us a value of acceleration for when it's being pulled up by 125 newtons of 11.85 meters per second squared. Meters per second squared. Meters per second squared, just making sure. And again, this is only the acceleration from the reference of the pulley. So this is just this A and that A. We want the full A, which is just putting the acceleration of the entire system, which is n over 7. In this case, 125 over 7. I'm going to draw down here. 125 over 7. And then plus 11.85. So this will give us the value of mass 1 in problem 2. And the value for acceleration of mass 1 is going to be 29.71 meters per second squared. So I'm going to write that over here, 9.71 meters per second squared. For mass 1, that's the acceleration when we're pulling up with 125 newtons. 125 newtons, not 120. So next, we're going to take this same value of acceleration, and now we're going to check what mass 2 would equal. Because mass 2 was the heavier one, so it was going down with this acceleration, and still being pulled up with the acceleration of the total system, which is 125 newtons over 7. So now we're going to just subtract 11.85. And so these are both values of acceleration. So that means I write my answer, which is around 6.00 meters per second squared. Write it in meters per second squared. So that means m2 equals 6.00 meters per second squared. We can put a box around that. So to recap, basically, after learning what a force is, what tension, weight, and acceleration, and gravity are, basically we use that to put use to these free body diagrams, and then with these free body diagrams, we checked our references, which allowed us to see what the reference where we need the acceleration with a reference of the ground would be, and then that allows us to solve our problem using all these methods, using algebra after we set up our equations, using Newton's second law, F equals ma, and then this led us to values of 16.44 meters per second, 0.696 meters per second for question 1 when it's being pulled up by 60 newtons, and for 125 newtons, values of 29.71 meters per second squared for mass 1, and mass 2 is 6.00 meters per second squared. So, thank you. Eesh.